1. Supervised learning. In supervised learning, models train on a labeled dataset where each example is paired with an explicit output label. The model learns to predict outputs based on input data. Imagine you have a bunch of fruits, each labeled with whether it is an apple or a banana. These fruits and labels serve as input data for a machine learning model to learn from. The task of the model is to learn to distinguish between apples and bananas by analyzing the features of these fruits. In classification, such as spam detection, the model learns to identify unwanted emails. In regression tasks like house price prediction, the model evaluates various features of homes to estimate their market value. 2. Unsupervised learning. This learning paradigm involves training models on datasets without labeled responses. The goal is to understand the underlying structure or distribution of the data. Imagine you're at a garage sale with a huge pile of assorted toys. Your job is to sort them into groups without knowing the categories in advance. You might group them by type, color, or size based on patterns you notice. Clustering, such as customer segmentation, where the model organizes customers based on purchasing behavior. Dimensionality reduction, such as principal component analysis, where the model reduces features for better visualization and data analysis. 3. Semi-supervised learning. Semi-supervised learning combines a small amount of labeled data with a large amount of unlabeled data during training. This method bridges the gap between supervised and unsupervised learning. Think of learning to identify plants where you only have a few labeled examples in a vast forest of unknown species. Using the traits from the known plants, you make educated guesses about the unidentified ones. Image classification. A base model is first trained on limited labeled images and then applied to unlabeled data to generate pseudo-labels. The original labeled data combined with high-confidence pseudo-labels will be used to train an improved classifier, enhancing the model's ability to recognize and classify new images effectively. 4. Reinforcement learning. In this approach, models make decisions and learn from the outcomes of their actions to maximize some reward in an environment. It's like teaching a dog new tricks by using treats. If the dog performs the trick correctly, it gets a treat, reinforcing the behavior. Similarly, the model learns to make decisions that will maximize its rewards. In gaming, such as AlphaGo, the system learns winning strategies. Autonomous vehicles use this approach to make driving decisions that optimize safety and efficiency. 5. Self-supervised learning. A type of unsupervised learning where the model uses input data to supervise itself and predict one part of the data from other parts. Imagine doing a jigsaw puzzle where you use sections of the puzzle you've already solved to figure out where the other pieces fit. Word embeddings, where we randomly mask out several words in a sentence and predict them based on their context. And autoencoders that learn to compress and decompress data, capturing the essence of the original input. 6. Meta-learning, often described as learning to learn. Meta-learning involves training a model on a variety of tasks so that it can learn new tasks faster with fewer data. Think of a decathlete in sports who trains across 10 different athletic events. By mastering multiple disciplines, the athlete becomes adept at adapting skills from one sport to improve in others, much like a model trained in meta-learning. Few-shot learning, where a model is trained to recognize new objects or categories with very few examples. Another example is learning to optimize, where the meta-learner learns to adjust the learning rate, architecture, or other hyperparameters to improve the learning process of the base learner. 7. Ensemble learning. Ensemble learning techniques combine predictions from multiple machine learning algorithms to produce a more accurate prediction than any individual model. It's like a council of experts where each member brings their unique expertise to solve a problem. By pooling their insights, the council reaches a better decision than any expert could alone. Random forests, where many decision trees make a collective decision, boosting algorithms like XGBoost, which iteratively improve their predictions based on the previous ones. 8. Few-shot learning. A subset of meta-learning, few-shot learning focuses on training models to make accurate predictions with very few training examples, often by leveraging prior knowledge. Imagine a seasoned chef who can taste a dish and then recreate it with minimal reference to a recipe. Their extensive experience allows them to achieve a high level of accuracy with little information. Facial recognition systems that accurately identify a person from just a few images. 9. Zero-shot learning. Zero-shot learning enables models to correctly make predictions for tasks or classes they have never seen during training, using an understanding of task or class relationships and attributes. Imagine a child learning colors. They see red, blue, and yellow. Then, they can guess a new color, like orange, because it mixes the familiar ones they know. Zero-shot learning is like that, using what you know to understand something new you've never seen before. Image classification models that can recognize new objects they were not explicitly trained to identify, like identifying a specific breed of dog they haven't seen before. 10. Transfer learning. Transfer learning involves reusing a pre-trained model on a new, related problem. It includes fine-tuning a model trained on one task for performance on a second task. It's like a professional switching careers. A teacher who moves into counseling may not need to start from scratch, but can adapt many skills from teaching to the new role. Using models pre-trained on large datasets like ImageNet to perform specific image recognition tasks that are not covered in the training dataset. 11. Active learning. Active learning is a technique where the model actively queries a user or an oracle to label new data points with the desired outputs, particularly useful when labeled data are scarce. It's like a scientist conducting experiments and choosing specifically which experiments to run based on the most informative results they need. Interactive document classification, where the model asks users to label the documents it is most uncertain about, improving its learning efficiency. 12. Online learning. In online learning, the model is updated continuously as new data arrives, one instance at a time, which is ideal when data is too large to process at once or continually evolving. Imagine a stock market analyst who updates their predictions based on each new piece of financial data throughout the day. Recommendation systems that adapt to changes in user preferences in real time are stock price prediction models that update their forecasts as new market data comes in. 13. Multitask learning. This learning paradigm trains a model on multiple related tasks at the same time, using a shared representation to improve performance on all tasks by leveraging the commonalities across them. Think of a multitasking office worker who handles emails, phone calls, and document editing, getting better over time at all tasks by understanding how to efficiently switch and apply skills from one task to another. A neural network trained to recognize both objects and colors in images, improving its accuracy in both tasks due to shared learning strategies. 14. Curriculum learning. Curriculum learning is a strategy where training data are presented in a structured or progressive manner, starting with easier examples and gradually increasing the difficulty. This approach is inspired by the way humans learn. Think of how we educate children, starting with simple concepts like numbers and letters, before moving to complex topics like algebra and essay writing. The gradual progression builds a foundation that makes learning complex ideas easier, teaching models to recognize complex patterns in images by initially training them on simpler, related patterns. This could involve starting with basic shapes and colors before advancing to detailed object recognition. 15. Contrastive learning. Contrastive learning is an unsupervised learning technique that learns representations by contrasting positive examples against negative examples. It's often used in scenarios where explicit labels are not available. It's similar to learning to distinguish between ripe and unripe fruit by comparing their features. You get better at recognizing the ripe ones by also understanding what makes a fruit unripe. Developing visual recognition models that learn to differentiate between pairs of images, identifying which features distinguish one from another, such as distinguishing cats from dogs based on their shape and size without explicit labeling. 16. Multi-instance learning. Multi-instance learning is a variation of supervised learning, where one label is associated with a set of instances instead of an individual instance. During training, the algorithm learns which instances contribute to the set being labeled positively or negatively. Imagine a bag of assorted candies, where the bag is labeled as good or bad based on the candies inside. You learn to predict the label of the bag by figuring out which types of candies typically lead to a good or bad rating. Drug activity prediction, where a model learns from collections of molecular structures and determines which combinations are likely to indicate effectiveness of a drug. 17. Federated learning. Federated learning is a machine learning approach where the model is trained across multiple decentralized devices or servers holding local data samples without exchanging them. This helps preserve privacy and reduces data centralization risks. Think of a group of chefs around the world who improve a recipe by trying different variations in their own kitchens and sharing only their cooking tips without revealing their secret ingredients. Predictive text and autocorrect features on smartphones that learn from user interactions without sending sensitive data to a central server. Privacy-preserving data analysis in healthcare, where patient data does not leave the local hospital's servers.